Okay, right. So if we increase our number of predictors, so the data space increase exponentially. So for example, if you have a 5 dimension, 5 variable, so data space will be 32 different data point. If you have 10 variable, I think it's a 1024 maybe, right? So the data space will be increased exponentially, right? So the Occam's razor, this is very famous the quote to talk about the dimensionality reduction. So if there are various logical ways to explain a certain phenomenon, the simplest is the best. Okay. Let's say we have 20 variables. Should we use all 20 variables? What if we can use only two components to explain the 20 variable? That'd be a better approach, right? In terms of, according to the rule of parsimony. So this is called curse of dimensionality. Okay. So the curse of dimensionality, why this is problematic? So as you can see, if the dimensionality increase, at some point, your model performance, statistical model performance increase, right? But at some point, it will be decreased. Okay. You already took 611 or regression analysis. So how did you learn? If you put more variables into your models, your R score will be increased, right? So theoretically, it will be increased, but if you put more and more variables, so you will have a lot of unnecessary variables, right? And also that means it will increase the probability of having noise in data. Okay. So your variable could have a lot of measurement error or bias or noise, right? So those will degenerate the model prediction performance. And also increase computational burden for training or applying prediction models. So, I mean, if you have only 10 variables, that should be fine. But in the big data analysis, sometimes you have 100 variables, 1,000 variables, right? In that case, it takes a really long time. Okay. And also it requires more number of examples to secure generalization ability of prediction. Okay. To repeat your, to make a generalization of your prediction, you may need more data, more variable. Okay. So how can we solve this curse of dimensionality? First, you can use your domain knowledge, right? You can evaluate, okay, which variables are more important and which variables are not important, right? And you can remove them or you can select them. Definitely, you can use your domain knowledge. And then also you can use some advanced statistical techniques to regularization term. Okay, so I will more talk about this one. And then also you can employ a quantitative reduction technique. Any questions? No? Okay, so there are two different approaches to reduce the dimensionality. Um, First one is the variable selection. The second one is variable extraction. Let's say we have n variable, x1 to xn, right? So variable selection is simply we select important variables. Okay, so in this case, okay, x1, x5, x8. So out of n variable, we selected 3 variables. Okay, so this is typical regression approach. So when you learn about the regression analysis, so backward selection method or forward selection method or stepwise selection method, right? So they are all the variable selection approach. And the second approach is variable extraction. So variable extraction is not select specific variable. So variables extraction involves creating a new variable based on the linear combination of existing variables. Okay. So for example, using all variables, we can create one component. X1 is x2 plus x3, or xz2 is x4 plus x5 plus x6. So using the linear combination of each variable, we create a new component. Okay, so that is a variable extraction method. So here are some statistical approach for feature selection and the feature extraction. So feature means variable. So sometimes it is called the feature. So variable selection, feature selection, they are same. So backward, forward, and stepwise regressions, that they are very commonly used in regression analysis. And lasso regression, Ritchie regression, elastic net regression, those methods penalize unimportant coefficient, which means if we have, let's say we have the 10 for 5, x5, x6, okay, 7, okay? So instead of estimating all the parameter estimation for each variable, we penalize unimportant coefficient just to make 0, right? So if you make this one close to 0 or it's very close to 0 or 0, that means we will remove these variables, right? So those approaches are lasso regression, Ritchie regression, elastic regression. They are these methods are very commonly used in machine learning or big data analysis, but they are beyond the scope of this course. So I will just conceptually introduce, okay? And then feature extraction is principal component analysis. This is one of the most commonly used method. And then exploratory effect analysis. If you already took psychometrics class, that you learned about the exploratory effect analysis, right? So the EFA analysis, that is one type of a feature selection, a feature extraction method. Also partial least square method, that is another method. But in this course, we'll focus on the principal component analysis. And then after that, we'll talk about the exploratory effect analysis. Okay. So now I will briefly talk about the backward, the forward, and stepwise regression. Okay, this is a variable selection method. For the selection method, so we start from the no variable, okay? From the model with the no variable, and significant variables are sequentially added. So let's say we have a p variable, p variables, okay? And then we tested every single variable and then select the most significant variable, okay? And then add all the combination. So x1 added, x2 added, x4, x5 to the xn. And then we select the variable contributing to most significant result. And then we select, well, first we select x3 and x5, right? And then do the same thing again. And we add all different variables to the p, and then we found, okay, x1 contributes the most important the model prediction, so we select x1. Okay, and then do it again, and x8. Okay, and then if we test more to 4, and 5. And okay, if anything doesn't improve our prediction model performance, and then we stop. Okay, so this is forward selection. But once the variable selected, it will never be removed. Okay, once we select one variable, it will not be removed. It will always included in the sequential model. That is the forward selection approach. And then backward elimination approach. So it starts from the old variable. Okay, so we start from the how many? Six variable. We start from the 6th variable, and then we remove one by one each, and then test it. Okay, and then if any specific variable does not significant contribute to predicting model, we remove it. Okay, in this case, x2 variable is not significant, so we remove it. So we have it like x3, 4, 5, 6. And then do this process again. Okay, and then we remove it one by one, and then test it. And then, okay, now x2 is not significant, so we remove it. And then test it again. Okay, and then x5 is not significant, we remove it. And then we remove one by each, and then nothing, then everything is significant, important, and then we stop. Okay, so this is a backward elimination. So it's the same with the forward approach. The once a variable removed, it will never be selected again. Okay. So this is the backward elimination. And stepwise selection, this is a combination of forward and backward. Okay. From the model with the no variable, it conducts forward selection first, and then backward elimination alternatively. Okay. So it tests forward and backward and forward and backward. So for example, so it takes a long time, then forward selection and backward selection. But the limitation of a forward selection and backward selection is once variable is selected or removed, they will never be added or removed in the model, subsequent model, right? So, but a stepwise selection, it tested all the combination of your variables. So the variable that is either selected or removed can be reconsidered for the next selection or removal process. So number of variables increase in the early period, but it can either increase or decrease. So here is an example. So we have a P variable, right? And then first we select, this is the forward. Thanks. And then because we have only one, we need to run another forward, right? And then we select 5, right? And then we do a backward again, x3 and x5, but we remove it. And in this case, x3 and x5 both are significantly important, so we keep it, and then forward again, add again, and then test it, and then 3, 5, 1, and O. And in this case, x3 is not important, so x3 goes out, and then we have only 2, right? And then forward again, so we add 7, and test the backward again. Okay, 3 things are all important, we keep it. And then forward again, and the x6 is included. Okay, so in this way, so if there is no significant improvement of your model fit, and then we stop. Okay, this is the stepwise selection. We start from the forward selection, and then backward selection again, forward, backward, forward, backward. In that way, we can test it. We can also test it already selected variables. Does that make sense? Because for example, in this case, X3, X5, X1 are selected, but backward and forward, they never test this selected variable again. But actually, X3 is important in this combination, but in this combination, X3 may not be important because of any unexpected interaction between X1 and X3, or X3 on X5. Okay, so in the X3 goes out. So this is the stepwise selection. Okay, so these are example of variable selection approach. Okay, but our main focus is in feature the variable extraction method. Okay, so principal component analysis. So what is principal component analysis? Principal component analysis involves a mathematical procedure transform a set of correlated variables into a smaller set of uncorrelated variables. So actually this variable is principal component. Okay, so it's called principal component. These PC principal components are linear combination of the original variables and can be thought of as a new variable in the subsequent analysis. Okay, so this is definition of a principal component analysis, but we'll more talk about these elements. So what is objectives of a PCA? So it reduces high dimensionality. So it is very good for visualization and interpretations. So if you have a high dimensional data, so 10D or 20D, it is impossible to present visually, right? The highest dimension of a visualization is a 3D, right? So 1D, 2D, and 3D. More than 4D, we cannot make a visualization, right? So if you want to make a good visualization, in that case, you can reduce the dimension and then make a plot. It is much easier to communicate with your audience. Okay, and also you can discover the true dimension of the data. So all variable, even though you have many variables, all variables are not important. Maybe some variables are unimportant. In that case, you can find the true dimension, okay, of your data. And also you can, and then you need to interpret the PC. The PC is the linear combination of original variable. Okay. So this is kind of hard to interpret the PC, and this is a limited this is kind of a criticism of principal component analysis, because sometimes it is hard to interpret the PC. So, okay, we found the 3 different principal components. So what does that mean? What does each principal components mean? So sometimes it's hard to interpret. So we'll see an example. Okay, so this is PC. This is multivariate data. Let's say we have a P predictors and then N observations, right? We have a P, but we reduce these all variables into 2 different components, okay? Or 3 different components. So this is the principal component. These principal components are they are the linear combination of all observed variable. So here is an example of a data reduction. So this is a 3D. Let's say we have some data like this, right? So this is 3 dimension. So if you want to classify this data set into 2 parts, it's pretty obvious, right? Maybe we can classify this one group and this one group, right? So this is a 3 dimension. But if we reduce 2 dimension data, we can reduce like this. This is one group and this is another group, right? And then if we reduced the 1 dimension, this is 1 dimension, one group is another group, right? So we can still keep the important information, but by reducing the dimensionality, we can make more easy classification analysis or prediction analysis. Okay. This is an example. So now PCA overview. So you will see some mathematics here, but I will explain it as easy as possible. So here, so like I said, Z is a linear combination of original all P variables. So this is the first component, right? The first component is, this is X1 variable, X2 variable to the XP variable, and they are all the coefficients, right? So this linear the principal component is a combination of all linear the variables, and then these alpha, they can be noted by the matrix formula. And X is the matrix of all variables, and this is the coefficient vector, transpose of coefficient vectors. They're the same thing. And then you can create another principal component using another set of the variables, and then another principal components using the same thing here. So theoretically, P variables, so I'm sorry, we can create P, in this case, we have a P variables, right? We can create P principal, we can create principal components using P variable, right? So if you have a 100 variables, if you have a 100 variable, so theoretically we can create 100 different principal components. Does that make sense? But our goal is to reduce the dimension. If we use the 100 principal component, why do we run the principal component analysis, right? So even though we can develop the 100 different principal component, we can just select 1 or 2 or 3, the most important, the principal components to explain all the data. Okay. And more example here. So let's say we have the 2-dimension data. Okay, let's say we have a 2-dimension data. This is 2-dimension data. And then I want to reduce 2-dimension, this is 2-dimension, to 1-dimension. Okay. So first, you can project, right? You can project all the data point to this axis, right? And then also you can project, you can find this axis and project all the data point, right? Do you follow me here? So another example, more example here. We have this data, okay, this data. And then I find the axis to explain this data to reduce the dimension. Okay, so basically, actually this data is two-dimension. Oh, I'm sorry. So this is two-dimension data, x1 and x2. Okay, so we have two-dimension data, and I found the axis, and I project all the values to this line. Okay, and then I find another axis, principal axis, and then project like this. Okay, and then if I make this one, if I rotate a little bit, so this is 1D dimension data, right? So this is 2D dimension data, and this is 1D dimension data. And this is 1D dimension data. This is 2D dimension data. We'll reduce it. And then after projection, the which principal component has a greater variance? So this is PC1, this is PC2. The principal component having larger variances of data is a better option. Okay, so which principal component is a better option? 1 or 2? 1, right? 1, because 1 has a larger variance. Okay, so that means this principal component includes more information, capturing more information of your data. If the variance of this principal component is 0, that means this is constant, right? Constant has 0 information in your data set. It doesn't explain anything. We want the data, so we want the principal component explaining larger variance of your data set. Okay. So, do you follow me here? Oh, good. Okay, so now we will move on to more mathematical stuff. Come on. So this is our P variable, right? This is N sample size. So this is our data, right? So this would be N by P matrix format, right? And then based on this data set, we can get the mean vector. So this is the average of these values. The X bar 2 is average of X2. Okay, in that way, we can create mean vector, right? And this is covariance matrix. So we can create the covariance matrix. We can get the covariance matrix based on this data set. And then this is correlation matrix. So orthogonal is all one. Okay.
So, Phil. This is where PCA differs from factor analysis, in that there's like 1 on the diagonal as opposed to like commonalities among the.
Not exactly. So the PCA, the most important difference between PCA and the EFA factor analysis is the PCA only allows orthogonal rotation.
Okay.
The first factor and second factor is always orthogonal. But the EFA factor analysis allows rotation, the oblique rotation or some other types of rotation. And also the EFA take into account the measurement error part. But the PCA, all the variances are common variance.
Yeah, so it could be error variance.
Yeah. So we'll more talk about that in the when I teach EFA. Okay. So this is overview of PCA algorithm. So step one, normalize data. So we need to normalize the data set. So in this case, I standardize it. You have original data, standardize it. Okay. So because the PCA is calculated based on the variance, right? So if you have a different the unit, we cannot directly compare the variances between the different units, right? So it's the first step one is to normalize data, but step two, you need to compute covariance matrix of original data set. But if you use if you want to use a correlation matrix, you don't need step one, because if you use the correlation matrix, that means the the covariance matrix are already scaled, right? So step one and step two. Step three, then compute eigenvalue and eigenvector using the covariance matrix or correlation matrix. So we talked about the eigenvalue and eigenvector, right, in the matrix. So you need to compute, the computer will compute the eigenvalue and eigenvector using the covariance matrix or correlation matrix. And step four, and ordering eigenvalues and corresponding eigenvector. Okay. So in this case, if we have a 5 variable, we will have 5 eigenvalue. If you have a 3 variable, we'll have 3 eigenvalue. If you have a 10 variable, we'll have 10 eigenvalues. Okay. In this example, let's say we have a 5 variable. Okay. That we compute eigenvalue and eigenvector using 5 variable matrix, 5 by 5 matrix, and then find all eigenvalues and order. Okay. And then also we can order corresponding eigenvector. Okay. And then compute the Z. This is compute the principal component using the eigenvector. So this is principal component, right? So we have a 5 variable, x1, x2 to the x5. And our goal is to find the coefficient, right? So these coefficients are eigenvector. Eigenvector of the first eigenvalue. Okay. So we'll see more example later. And the second axis, a second principal component, these coefficients are eigenvector of second eigenvalue. And fifth, these coefficients are eigenvector of fifth eigenvalue. Okay. So, and then we can summarize this relationship like this, right? Z is our principal component. Alpha, this is all the coefficient, right? And then transpose, so that is the coefficient matrix. And the X is these are all the random variable, X1 to X5, right? X1 to X5. And then we'll go one step further. Okay, assume we have normalized the data, and then we just show this relationship, right? So X is random variable with the covariance matrix. Alpha is a p-dimensional vector. This alpha is what? This is coefficient, right? Coefficients. So main purpose of a PCA is to find alpha. that produced the largest variance of X. Okay. So Z equals alpha transpose X. This is a coefficient, right? So the main purpose of PCA is try to find alpha that produces the largest variance of X. Okay, so we need to find these values, and then this is what? How can we find alpha? Alpha is eigenvector of the covariance matrix. So here is an example. We have 3 variables, x1, 2, 3, right? x1 is 0.2, 0.45, 0.33, 0.54, 0.77. x2 is 5.6, 5.89, 6.37, x3, 3.56, 2.4. So they have all different units, right? So we need to normalize first. So we normalize it, x1, 2, 3, by standardizing. So mean is 0 and variance is 1 in this case, right? And then we can compute covariance. This is covariance and this is correlation. Okay. So this is covariance. And then now, so eigenvalue and eigenvector pairs on the correlation matrix, covariance matrix in this case. So this is a 3 by 3 matrix, right? So if let's say we find the eigenvalue and eigenvector of this matrix, and then let's say first eigenvector value is this one, and the eigenvector is this one, and second eigenvalue is this one, and second eigenvector is this one, and third eigenvalue is this one, and third eigenvector is this one. Okay, so let's assume we find the eigenvalue and eigenvector of this covariance matrix, correlation matrix. Okay, so far so good. Okay, so first, we just found the 3 eigenvalue and 3 eigenvector, right? So this is among 3 eigenvalues, which eigenvalue is the largest? Third one, right? Eigenvalue, this is 2.76, and second eigenvalue 0.16, and third eigenvalue 0.08. I rounded. Okay. And then this is our normalized data set. Okay. And then let's try to build our principal component equation. So first one, so this is principal component is, this is a coefficient, this is a random variable. We have 3 variables, right? So variable 1, variable 2, and variable 3. This is the first. What is the first principal's coefficient? This eigenvector. Here, this eigenvector. Here, this eigenvector is here. Do you follow me? So this equation is the first principal component. Okay. And then if we add, this is x1 data, right? If we add this data here, so right here, and then this is the second data, third data, and if you compute this one, you will get this one. So this is principal component scores. Okay. This is called principal component scores. This is the principal component equation. This is the principal component square. Okay. And repeat the same process to the X2 and X3, a Z2 and Z3. And then we can get this principal component score and this principal component score. So let's do this. Z2 is equal to, what is it? X1, X2, X3, right? So Z2 is just, this is the second eigenvalue, second highest eigenvalue. So coefficient will be the eigenvector of plus this one, 1.43, right? And then if you input these X1, X2, X3 data to here, and you will get this principal component score. Okay. And then do the same thing. And this is G3. This is third principal component score. And then we have Z1, Z2, and Z3 principal component score. So Z1, Z2, Z3. This is principal component score matrix. Right. So are you okay? Are you okay with that? So far, so good. So here is it. Origin. Let me erase. We have X1, X2, and X3, 3 variables, right? And then finally, we found Z1, Z2, Z3 variables, principal component scores, right? So we have 3 variables. So Z1, Z2, Z3. And okay, let's say Z1 explains most of our data set. So I will select only Z1. Okay. So in that case, we can use this Z1 score for the further analysis. If you want to run regression analysis, we'll just use this data, this variable, not using this original data set. Okay, so these scores are transformed principal component score. Okay. So here, okay, and then here is very important, the characteristics of a principal component. So this is principal component first score, right? And principal component the second score, principal component the third score. And then if we get the covariance matrix, this is covariance matrix. Okay, so what is the covariance of, this is Z1, Z2, and Z3. What is covariance between Z1 and Z2? What is this? 0. What is covariance between Z2 and Z3?
They're all 0.
0, right? But covariance between Z3 and Z1 is 0 and 0. Okay, so that means all the principles are orthogonal. Okay, so all the principles are orthogonal. So for example, we have found, so here is some data, and we found the first principle, and the second principle is orthogonal, should be orthogonal, perpendicular. PC2, okay? If we add one more PC, that will be a 3-dimension. So I don't know how to draw, but that will be orthogonal like this. Okay. So the principal components are orthogonal. This is a really important characteristic because in many cases, PCA is used to reduce the multicollinearity problem. If you have many variables in your data, in the multiple regression analysis, so you may have some multicollinearity problems, right? So for example, the satisfaction, job satisfaction, life satisfaction, work family satisfaction, all the satisfaction will be very highly correlated each other, right? So how can we deal with that? One approach is to use the PCA, okay? But if we transformed the multi-collinearity variable to principal component, and those components will be orthogonal, unrelated. So in that way, we can address the multi-collinearity problem. Okay, so why multi-collinearity problem is important? Because multi-collinearity it increase standard error, right? So it's standard error, so that means it will increase confidence interval bound. Also, standard error, for example, your beta is, I'm sorry, t equals the beta divided by standard error. If this is increased, standard error is increased, right? Your t, this variable, is likely to be insignificant. Actually, this is significant, but your SE standard error increase, so it becomes non-significant. So we may have a lot of type 1 error. Right? These are statistical problems of multi-collinearity. So these issues can be addressed by using PCA.
Phil, quick question. On the covariance Z1 and Z1Y is 0.
Oh, I'm sorry. This one?
You're right, yeah.
Yeah, I'm sorry. This is not 0.
Okay.
We'll talk about this one in the next slide. Yeah. And now, okay, theoretically, we can extract the same number of component as many as number of variables, right? But how many principal components we should use? We extracted the 3 components. So how many we need to use, right? So here's an example. Let's say eigenvalue. So eigenvalue of covariance matrix that is equal to the variance of each principal component. Okay, so eigenvalue of a principal covariance matrix is equal to the variance of each principal component. So we have this data set, and we find this first Z1 and Z2, right? And then you can project all the data point to this axis or like this, right? So this amount of variance, this variance of Z1, this variance is eigenvalue of Z1. Okay, and then also this variance of Z2 is eigenvalue from the second principal component. Here's question. So do we want large eigenvalue or small eigenvalue? Large, right? Because the large eigenvalue indicates amount of variability of your principal component, right? So, okay, let's go one step further. And, eigenvalue of a covariance matrix, that is variance of each principal component, right? And this is covariance matrix of our principal component, right? All the covariance of each the axis are 0, and then this is the variance of each what? The axis principal component. So variance of each principal component is eigenvalue, right? So this is eigenvalue. Eigenvalue of PC1. This is eigenvalue, value of PC2. This is right here, eigenvalue of PC3, right? So here is some different notation. Oh, I'm sorry. You have the PC number is arbitrary in this case. So first principal component is the largest eigenvalue, so 2.756. Second principal component is the second largest component, 0.1618, and now the 0.07, right? And now we can compute the proportion of total population variance due to the first principal component. So total variance is this one, 0.078 plus 0.018 plus 2.75, right? This is total variance. So total variance should be 3 in this case because we have a 3 variable. Total variance is the number of variable because we assume each variance has 1, 1, 1, 1, 1. So the total variance is 3. But the first largest eigenvalue is 2.7596, right? So if you compute this, this is 0.92. So which means the first axis, first principal component explains 92% of your total variance of your observed data. So one principal component explains 92% of your data. That's a lot, right? So maybe, but the second eigenvalue, if you look at the second eigenvalue, it's pretty low. It's only 0.16. Maybe its incremental improvement will be minimal. So I may choose only one principal component in this case. Right. So how can we determine number of principal? There are a couple of different ways. So in this case, this is the first component, 92%, right? And the second component is only the less than 1%. And the third component is like this. So first approach is retain sufficient components to account for specified percentage of the total variance. So this is rule of thumb. So we generally select 70% or 80%, okay? If two principal components explains at least 70% of your total variance, that we will select 2 principal components. Okay, so in this case, single principal component explains 92%. So we just choose 92%. Okay. And then second approach is use eigenvalue. Okay. So we select eigenvalues that have greater than 1.01. Okay, so we have 3. We don't have eigenvalue information here, but if you go back, so we have only one variable is greater than 1, right? So the second eigenvalue is much less than 1. Third eigenvalue is much less than 1, right? So we will select only 1. This is the second approach. The third approach is a script plot. We just use a script plot, find the very elbow plot. This looks like elbow, right? So find the elbow, and then we can select that elbow point. But in this case, 1 and 2 components can be considered, but second component has a very low proportion of variance, and also eigenvalue is less than 1, so I would not choose this one. So select only one. Go. So there are 3 different approaches to determine the number of principal components. And same, these logics is applied to the EFA, factor analysis as well. So if you clearly understand the principal component analysis, EFA is really easy. So they follow the same logic and very similar. Okay. And then now let's talk about the PCA loading plot. PCA loading plot is quite useful to evaluate the impact of your each variable. So this is the first principal component. This is the second principal component, right? So this is the PC1 and this is the PC2, right? And then these are the coefficient, right? So these values, x-axis and y-axis represents the coefficient. Okay, so how can we interpret this? So first, let's look at the x1. If x1 increase, as x1 increase, x1 increase, the P1 value, this is the P1, right? So here is 0. It's right here, right? This is a positive. So principal scores on PC1 increase, and also this is positive, this is 0, this is a positive, right? So positive. So x1 increase, principal scores on PC1 and PC2 both increases, right? So it indicates x1 is an important variable to create PC1. Okay. For what if you have this kind of things? This is x1. If this x1 is here, you know, x1 doesn't really contribute to create PC1, right? x1 increase, PC1 increase this much, very minimal, and PC2 increase. So this x1 point doesn't impact the principal scores on PC1, right? What about PC2? As a PC2 increase, our principal scores on x1 increase, right? It's a positive. This is 0 and this is 1. It goes positive. But PC2 scores, this is 0, negative, right? So as x2 increases, the principal scores on PC1 increases and principal scores on PC2 decrease in this case. And PC3, x3, so as x3 increase, principal scores on PC1 decrease, minus, and principal scores on x2 is just slightly increase. Okay, so PCA loading plot is quite useful to evaluate the impact of your each variable on the principal scores. Okay, so in this example, we have only 3 variables, but if you have a 20 variable, 30 variable, 40 variable, and you see a lot of variables plotting here, right? For example, here, that means these variable doesn't contribute to your PC principal component development. So I would remove these variables to develop the new principal component. Okay, so this is kind of the evaluation plot. Okay, so what if you had 4 variables? So PC1 would spend the direction of most variation, right? PC2 would span the direction of second most variation. PC3 would span the direction of third most variation, and fourth will be the first variation, right? if you have 200 variable, how many principal components we can have? Theoretically, 200, right? But we never use 200 principal components. That we will, I mean, if you can use only 2 principal components, that will be huge. The contribution will be very efficient. Okay, so any characteristics of a PC principal components. Principal components are uncorrelated. The very important characteristics. And this is the main difference between the factor analysis as well. And the first principal components accounts for as much variability in the data as possible. And each successive principal component accounts for as much variability in the data as possible, okay? And the interpretation of a principal components. So coefficient of a PC should be interpreted, okay? We created, if you extract the 2 principal components, so, I mean, you need to interpret what those principal components are, what does components mean, right? The sign and magnitude of coefficients, for example, that coefficient, that principal component is positive and strong relationship with some satisfaction variable. Maybe you could interpret that principal component as the satisfaction. And another principal component has very, the positive, strong relationship with depression. Maybe you could interpret that principal component as a depression component that way. Okay.
So then at what point does that just become, I mean, I know mathematically it's a bit different, but become like a factor analysis?
Yep. Become like the factor analysis. So principal component analysis and factor analysis is very similar. So yeah. And principal component should not be rotated because it's orthogonal. If you rotate, you will lose some variance information. Okay. If you rotate, the variance of the principal component will not be eigenvalue anymore. And then for improved interpretation, you may wish to try factor analysis. You can also try factor analysis, and rotation does not destroy any properties in factor analysis. And PCA, okay, so PCA assumes multivariate normality assumption. So if the multivariate normality assumption is seriously violated, then you can try alternative methods such as kernel PCA or locally linear embedding methods, but they are beyond the scope of this course. But you need to know there are some alternative methods to deal with the non-normal, the distribution method problem. Okay, so possible issues with PCA. So, if the original set of variables are already uncorrelated, PCA will not help, right? Because the PCA tried to find the common relationship based on the combination of a linear relationship. But if your original set of variables are uncorrelated, a very low correlation, in that case, the PCA will not help. So before you conduct a PCA, definitely you have to check correlation first. And PCA does not generally eliminate variable because the PCA are linear combination of original variables. So PCA is a variable extraction method. This is not a variable selection method. So original number of a variable will not be reduced. Okay. And original variable need to be measured in the same unit, right? So you have to normalize, right? Or you can use correlation matrix. Okay, correlation matrix in place of covariance matrix. Okay. All right, summary. So PCA advantage. What is the advantage of a PCA? So first, it is very useful for dimension reduction for high dimensional data analysis, right? So for example, image data analysis, there are tons of dimensionality. So 100,000 times 100,000 metrics. So 0, 1, 0, 1, 0, 1, 0, 1. And also the text mining analysis, the data metrics, the dimensionality of data metrics is really huge. In that case, it's really important. And it helps to reduce the number of predictors, items that using principal components. It helps make predictor items independent, right? Make the relationship on orthogonal so it can deal with the multi-collinearity problem. And it allows interpretation of many variables using two-dimensional plot. So it's very useful to interpret the relationship graphically. Okay. And can be used for developing prediction models. And but PCA disadvantage, what are the disadvantage? First, it only works for numeric variables. Okay, if your variables are categorical or dichotomous, in that case, you cannot apply PCA. So okay, PCA only works for the numeric variables. The second, so prediction models are less interpretable, so which means sometimes it is very tricky to interpret the principal component. Okay, these are some disadvantage. Okay, so I think I will stop here. So in the next class, I will show you how to extract principal component and how to use principal components for the further analysis, okay, using R. Okay. Do you have any questions for principal component analysis?
One question here.
Mm-hmm.
So what are the advantages of PCA compared to factor analysis?
What is the advantage of PCA for the that's good and tricky question. I don't say one method is better than the other one. I mean, they are just a different approach.
Okay.
So instead of PCA, you can definitely apply the factor analysis. But the factor analysis, the main difference is the factor analysis. Factor analysis extract a latent variable. But PCA is deal with observed variable.
Oh.
Okay. So this statistically speaking, factor analysis is a more advanced approach than PCA. Okay.
Yeah.
PCA was first developed, but PCA only can deal with the observed variable. So the factor analysis can take into account the measurement error or some error part and extract the latent variable of observed variables. So they are the main difference. But I don't know which method is better than which one. It really depends. It really depends on your purpose. So if your variable is observed variable, you can just use.
Is there any situations that you could only use PCA but not factor analysis?
Any situation? I don't know. I mean, if you apply PCA, you can definitely use the EFA factor analysis.
Oh, okay.
Yeah.
Okay.
Yeah. But there are different approach.
Thank you.
Yeah. I mean, for example, you can apply the linear regression, and also you can apply nonlinear regression analysis, right? Right.
Okay.
So there are different approach to dealing with the same data set. But if your EFA analysis produce the better model performance, you can take a EFA rather than EA. But you just try both and compare the results and pick the better one.
Okay.
Phil, would you say that EFA, like where it's it's more theory driven. So
Yeah.
when you're like picking your factors, like making a new measure of
Mm-hmm.
maybe a multi-dimensional constructs, would it be appropriate to run a PCA?
Yeah, that's a good point. So yeah, so EFA is more appropriate for more theoretical, the latent construct, because the EFA, the fact analysis, extract the latent construct. So if you're dealing with the latent construct, in that case, EFA, fact analysis is more appropriate. But if you're dealing with the observed data set, but a PCA is totally fine. Like the money, income, age, so they're all the observed variables, right? So, and the reason why PCA is very commonly used in data science is, for example, the image data is always coded as 0 and 1, but dimensionality is huge. So that is not latent construct. So PCA will totally fine. But we'll more talk about the EFA after this class, after fact the PCA. So we will see more clear difference between these two. So good. Okay. Any other questions? All right. Okay. So I will stop here and have a great weekend. And if you have any question about your homework, email me and I will see you on next Tuesday. All right. Bye.
So,
Bye.
Thanks, Bill.
Thanks.